Hello, in this video we're going to look at limits at infinity, part 2. So just to remember, the square root of x squared is not actually equal to x. It's equal to the absolute value of x, or you can think of it as plus or minus x. It's going to be plus x when x is greater than or equal to 0, but it's going to be negative x when x is less than 0. And this idea that when you square root a square, you don't necessarily always get just x, you sometimes get negative x, is very important because we're going to look at doing limits at infinity when we have a square root. Now, let's look at this one to start. Of course, if you were to plug it in, you're going to get infinity and then a negative infinity, and you're going to need to do more work for sure. But one of the issues is we would like to use the quotient theorem. We just developed it, and it seemed very useful. So it'd be nice to get rid of the 2x and the 3, and it would be nice to get rid of the plus 1. And we can do all of that. We can get rid of all of those things, but we're going to need to get rid of the square root. And that's where the issue comes in. How do you get rid of that square root? Well, to do it, we're going to have to take the square root completely out of the limit. If you remember, the limit of a root is the root of the limit. And so eventually, we need to get a root down here as well. So our goal is going to be to get this root out, to get ourselves into just the polynomials, and to ultimately use the quotient theorem. So let's see if we can get that started. First off, we have 2x plus 1. We want to make that equal to a square root. So put a square root, put 2x plus 1, and square it. But now it's going to be technically plus or minus here, because the square root of a square is, well, plus or minus. So is it going to be plus or minus? Which one is it? Well, you investigate what's happening with the limit. X is approaching infinity. So the portion 2x plus 1 is definitely going to be positive. It's going to be, as x approaches infinity, x is equal to 100, 1,000. 2 times 1,000 plus 1 is a positive number, which means we take the positive square root. So we can write this as the limit x approaches infinity, root 3 minus 2x plus 5x squared over root 2x plus 1 squared. All right, well, we remember that when you have the square root on the top and bottom of a fraction, we can take that all the way out. So we have square root limit x approaches infinity, 3 minus 2x plus 5x squared over 2x plus 1 squared. So notice, if we were to forget about the square root for the moment, this portion here would just be the limit of a rational function over a rational function. This would be a perfect example of the quotient theorem. So we're going to go ahead and apply that. Limit x approaches infinity of 5x squared over 2x, all squared. So we keep going. We have, don't forget that square root. Limit x approaches infinity, 5x squared over 4x squared. We can go ahead and cancel the x squareds. That'll give us the limit x approaches infinity, 5 over 4. The limit of a constant is just the constant itself. So we have square root of 5 over 4, which we could write as square root 5 over square root 4, which would be root 5 over 2. And so again, the key to solving this problem is taking this denominator and making it have a square root, giving it some type of square root. And in this case, it was the positive. Let's go ahead and look at another one. Here we have the limit x approaching negative infinity of root 9x to the 6th minus x over x cubed plus 1. So same idea. We have the issue that it may be a positive or it may be negative square root. Let's go ahead and find out. So we take x cubed plus 1, and that's equal to, well, the square root of x cubed plus 1 squared. Now let's think about this. X is approaching negative infinity, so it's taking values like negative 100, negative 1,000. If you take negative 100 and cube it, it's still going to be a negative number. You add 1 to it, it's still definitely negative. So since this is less than 0, we have to take the negative square root. So when we rewrite this, we have the limit x approaches negative infinity, 9x to the 6 minus x over negative square root x cubed plus 1 squared. So we can go ahead and take that square root out, and there's going to be a negative that comes with it. And then we have the limit x approaches negative infinity, 9x to the 6 minus x over x cubed plus 1 squared. So we're going to go ahead and use the quotient theorem here to get the limit as x approaches negative infinity of just 9x to the 6 over x cubed squared. Now, when you have power to a power, of course, you multiply. So this is going to cancel with x to the 6. This gives us negative the square root, the limit x approaches negative infinity of 9. Well, the limit of a constant is just a constant. Square root of 9 is 3. So our final answer is negative 3. Now, I want to correct a quick misunderstanding that students sometimes get. You might have noticed that in the previous example, x was approaching infinity, and we took the positive. Here, x was approaching negative infinity, and we just so happened to take the negative. So you might be forming a little rule in your head. When it's positive, you take the positive. When it's negative, you take the negative. That is not true. And so we need to clear that up because it would be very disastrous if you encountered something like this. What if you had the limit x approaches infinity, and maybe part of your question had a 4 minus 2x squared? Well, you might be tempted to say x is approaching infinity, so I'll just take the plus. So I know that 4 minus 2x squared is equal to the square root of 4 minus 2x squared whole squared. And you would say, oh, I'm just going to clearly take the positive. But should you? Should you take the positive value? Well, this portion here, if we think about taking a really large value of x, like 100, well, 100 squared will be a large value. 2 times 100 squared, that's a large value. 4 minus that large value is going to be negative. And so this portion is actually less than 0, which means we don't take the plus, we actually take the negative. And so you need to be really careful. Just because x is approaching positive infinity doesn't mean you take the positive value. You always have to think about it. You have to reason out, as x approaches infinity, what's happening to this quantity? Is it becoming positive or is it becoming negative? Now, I promised in the last video that I was going to connect this to horizontal asymptotes. So a horizontal asymptote, if you remember from pre-cal, is this line horizontally that's involved in drawing graphs. But we never actually gave it a definition in pre-calculus. Here in calculus, we can give the horizontal asymptote a full definition. It is a horizontal line, y equals L, and it's called a horizontal asymptote if the limit as x approaches infinity of f of x is equal to L, or the limit as x approaches negative infinity of f of x is equal to L. So the horizontal asymptotes are actually defined as limits, as these limits as x approaches either positive or negative infinity. So as a remark, suppose we're sketching the graph of a rational function. We want to know what happens to the graph as x gets very large. For these large values of x, we know f of x will approach the asymptote L. But some of the asymptote knowledge that you have from pre-cal might be a little bit warped, a little bit skewed. So we're going to go through an example here. First off, we have y equals x plus 2 over x squared plus 1. What would be the horizontal asymptote? Well, we could go ahead and do our regular method. We would take the limit as x approaches infinity of x plus 2 over x squared plus 1. Using the quotient theorem, that would give us the limit x approaches infinity of x over x squared. We could, of course, simplify that down to the limit x approaches infinity of 1 over x, which would simply be 0. So therefore, we would have a horizontal asymptote at y is equal to 0. But what happens when you actually graph the function? Well, here we have a nice computer-generated graph, and we can go ahead and throw the asymptote on here. So we throw a dotted line. we can clearly see that the graph over here, as x approaches infinity, it approaches that asymptote. It's getting very close to that value. But what's happening over here at -2? It almost appears like the graph is crossing the asymptote. Well, let's go ahead and try. Let's plug in x equals to -2. So if we have our function y equals x plus 2 over x squared plus 1, if we plug in x equal to -2, we'll get y equals -2 plus 2 over -2 squared plus 1, which will be 0 over 5, which is just, well, 0. And so it looks like the graph has a value there. It looks like the graph equals the asymptote. Is that possible? Well, indeed it is. The graph crosses the asymptote. It definitely crosses. It passes through that line. And this is very, very important, that the graph crosses through the horizontal asymptote, because the horizontal asymptote is simply a limit. If you look back up here at the definition, it's just a limit. Sometimes you might have heard asymptotes referred to as magical lines that you can't cross, and that is an incorrect definition, and that is an incorrect assumption. There's nothing magical about an asymptote. It's simply a line that the graph will approach as the values get very, very large. -2 is not a very large value, and so there's no reason the graph shouldn't approach or pass or cross the asymptote over here. It's only when x becomes very, very large, or if you were to go the other direction, very, very negative, that the asymptote will have any effect on the behavior of the graph. Now, let's go ahead and look at the limit x approaches infinity 1 over x times sine x, because I really want to help you understand this, help you grasp this point, because sometimes it's not always grasped in earlier courses in mathematics. Let's see if we can figure out this limit. Well, if we were to plug it in, 1 over infinity would give us a 0, but sine of infinity doesn't make any sense. So we're going to actually use the squeeze theorem here. We know that sine x is between 1 and -1. And we can go ahead and divide the whole inequality by x. Now, if you think about it, 1 over x times sine x, that's the same thing as sine x over x. But don't go thinking that this limit is going to be 1. That's only when x approaches 0. In this case, when x approaches infinity, we have to look at either side. So the limit x approaches infinity of -1 over x, that's going to be 0. And the limit x approaches infinity of 1 over x is also 0. So we can say, therefore, by the squeeze theorem, the limit as x approaches infinity of 1 over x sine x is equal to 0. And so apparently we have a horizontal asymptote at y equals 0. Let's go ahead and take a look at what the graph looks like. So here we have the graph of 1 over x sine x. It's quite an interesting graph. It seems like it oscillates back and forth. But as you go further and further and further along the graph, it seems like those oscillations, they get smaller, they kind of die down. And you can see that as you go further and further and further along, the graph is indeed approaching the asymptote. It's approaching the value y equals 0. But the way it's approaching that value is very strange. It appears like it's crossing here at pi, and then crossing at 2 pi and 3 pi and 4 pi and so on. In fact, this graph will cross its asymptote infinitely many times. It will cross the graph forever. The graph and the asymptote, they are not repelled by each other. It's not some magical line that can't be crossed. In this case, it crosses over and over and over. It's always crossing. It's just that it's approaching that line. Now, this might seem very strange for you, but you could think of an analogy. I'll give you a picture to hopefully jar your memory. Think of those swinging doors in a Western movie when they walk into the saloon. As the person walks past the door, well, it swings open. and then behind them it swings closed. But it doesn't just stop there because the hinges are a little bit loose and it's been there for a long time. So the door, it swings back and forth and back and forth and back and forth as it settles down. If you were to visualize this on a graph, what's happening is the x-axis is the position of the door when it's perfectly closed and not moving. And when someone walks through, it's as though the door is now open, and then it closes and opens and closes and opens and closes. But now over time there's some friction and some air resistance, and so the door, it oscillates less and less and less, and eventually by the end you could say the door eventually is fully closed again. And what that means in the mathematics is that the limit, as x approaches infinity, as you wait long enough, as you give it enough time, eventually the door approaches that position of being closed, but it crosses the closed position infinitely many times along the way. Of course it can cross the position. It's not a big deal in the real world for the door to cross that closed position. So you really don't want to think about asymptotes as these magical lines that you can't cross. It's not true and it's not helpful. So a quick multiple choice question here. Can you cross a horizontal asymptote? No, yes, maybe, or pi? Well, of course, the correct answer is yes. So one more question here, again related to the other one. Determine the limit as x approaches infinity of sine x. So go ahead and pause the video and give this a try. All right, so if we think about the graph of sine x, this one oscillates forever and ever, and it doesn't settle down, it doesn't approach a fixed value, which means that as x approaches infinity, well, sine x, it just continues to go between -1 and 1. So it doesn't have a limit in this case. It doesn't have an asymptote, which means that the limit does not exist. So for homework, you can do the limits at infinity part 1 worksheet. You can do the square roots now. So before you couldn't, but for this portion here, you can now do the square roots. And you can also do part 2. There's a second worksheet as well. You can take a look at some questions in the textbook on page 135, 15 to 35, 37, and 39. And we're also now done chapter 2. And so this is the end of the first unit. We're done with limits. Well, not done with them. We're going to use them heavily in the next chapter. But we're done with the section on limits. And so you can look at your chapter 2 review, which reviews the main concepts from the section on limits. So hopefully you enjoyed this video. And as always, thanks for watching.